How's that? Can you hear me and see the slides?
Yes.
Okay. Thanks very much to the organizers for their perseverance as much as anything. Thank you for the opportunity to give this review talk. And I am very much looking forward to learning all sorts of things, particularly about the Milky Way, where I think there's enormous amounts of synergy and opportunity for me to learn more about Bulges by knowing more about the Milky Way system. So what I'm going to try and do in this talk is give a bit of perspective, which is going to start very basic, and then try to convince you of maybe a few things that may eventually become slightly uncomfortable, which is why all high redshift star formation is spheroid formation. And let me just let some of you digest that to start off with until I try to build up towards that argument. A couple of practicalities. I'll then go through a couple of recent results and trends, future directions, and then get back to the summary. Hopefully you can see the cursor as well on the screen. So let me start off with my talk is Bulges in a cosmological context. What do we mean by that? We're really interested in looking at where most of the stellar mass in the universe resides, in what kind of structures, in what kind of form. How has that mass grown and come about? And so we're following not necessarily the most numerous system or the most common system, but we're trying to follow the mass, the way people talk about follow the money. We're trying to follow the mass and see where most stellar mass resides. We're also interested in the photons. We're also interested in the typical photons that are flowing through space and asking where those photons have come from. Mostly it's star formation or AGN activity, and that's the indicator that tells us maybe how those structures are formed and when those structures are formed. And ultimately, we're trying to get to the dominant mechanisms that have transformed the mass and generated this energy over the entire cosmological time frame, and trying to identify if there are multiple mechanisms, which mechanism dominated over each period and what that period is for. So that kind of is the motivation for where this talk is coming from, which is in many ways sort of overview, big picture, and not directly drilling down to very, very detailed formation mechanisms, but trying to understand where is all that mass, where is all the energy, what are the key timescales of things that happen. Traditionally, most of the stellar mass resides in ellipticals and massive early type spirals. And so we essentially have this scenario of spheroid only, spheroid plus disk systems and disk only systems. And naively, galaxies can be defined as basically with this two component terminology. And I know that there are many of you out there that study bars and pseudo bulges and boxy peanut and so on. And I think a really interesting question I'd like to establish is whether they are secondary structures, whether we really have two primary structures, which is the classical spheroid and the classical disk system, and whether the structures like bars, spiral arms, pseudo bulges, peanut and boxy cores are something that we actually consider secondary structures that are formed from the disk. And I raised that because I read one interesting Gaia paper that seemed to suggest some of the bar of the Milky Way has actually formed from the original bulge stars as well as the disk stars. And that was completely new to me. So I'm kind of interested from the Milky Way side of things, whether this concept that we have two primary structures and then a myriad of substructures that are formed from the disk is actually something that most people would sign up to and agree. So in terms of defining what I mean by the spheroid, it's the compact triaxial high surface brightness structure, typically dominated by an old stellar population, is dust-free, inert with very little star formation, except perhaps occasionally in the core. It's a pressure-supported system. Often it might be alpha enhanced, implying a very rapid formation, and generally has minimal substructure, although of course there may be nuclear disks and a nuclei. And on the disk side, we have the flattened extended diffuse systems, medium to low surface brightness, intermediate to young stellar populations, often dusty, often star forming, rotationally supported, age and metallicity gradients, and often exhibiting quite significant substructure where quite a significant amount of the disk mass may be in bars, spiral arms, and in these other structures. So that's our starting point. And if you buy that starting point that we have two fundamental structures and then some substructures, then we have to go through the process of decomposing, because if we've got two different physical mechanisms that are at play, and they may have operated over different timescales, we're only going to unveil that or reveal that if we start looking at how the properties of spheroids and the properties of disks have evolved distinctly, even though they may be within the same galaxy. The analogy I like to make is a little bit like coming down and understanding a car. If you want to come down and try and understand a car, you can measure their colors and their shapes and their sizes, but at some point you've got to understand what are the critical components, the engine, the chassis, the frame, and so on. So in my world, we have two distinct components and a myriad of substructure. Now, the first thing I want to get into is bimodality, because bimodality, came through as something we kind of knew, but was reinforced through the Sloan Digital Sky Survey with classical papers from Strativa and Bulges. And one of the things that's been forgotten a little bit is that, I think, is that both of these things were originally framed in terms of color and concentration. So we don't just have a color bimodality, although we do clearly see that, but we also have another axis of concentration. And we could see that the two populations, the red and the blue, are offset in concentration. And Bulges showed the same thing, that as well as having that color offset, we have a concentration offset, and how it shifts as we go from blue to red. We see a shift, not just in color, it's not just a horizontal shift, vertical shift, but there is a horizontal shift as well in concentration. And we found this as well when we plotted the Sersic index of the individual galaxy components, that we had two peaks that were offset in this plane. And this is really important, because if this is true, you can't go from the blue cloud to the red population without undergoing a structural change at the same time. And I think there must have been, since these papers have come out, there must have been hundreds, if not thousands, of papers that talk about transformations of the red population from the blue population through the Green Valley to the red population, perhaps back and forth and so on. And they're always talking about color. And this notion that along with that color change, bimodality is also defined by fundamental structural difference is often ignored. And why is that important? It's important because structurally, the shape of the galaxy is defined by the orbits of its billion or 10 billion stars that make up that structure. Changing the color is potentially quite easy. You can shut off the star formation, you can quench the galaxy, and the color will change. But it's not obvious that quenching will change the orbits of a billion stars from a diffuse distribution to a concentrated distribution, or change the Sersic index. Well, maybe that's not quite true, but structural transformation certainly is hard. And shifting billions of orbits to change the structure is not easy. Just switching off, just quenching star formation may not turn this disk galaxy on the left into a triaxial structure on the right. After saying that, there are some combination of factors that can help. If you shut down star formation, if you remove the dust, the disk light is suppressed, and the bulge potentially, if there is a bulge component, can emerge. And the overall shape then may change. So if you have a suppression of star formation, a removal of dust, if you're able to strip the edges, which might involve the infall of a galaxy into a halo, then a bulge may emerge and some structural change may take place. And this may be the pathway by which SAs turn into S-series and ellipticals. The idea basically is that it's not easy. And so you probably have to have a major merger or the infall of a galaxy into a cluster or group environment in order to actually have a transformation from the blue cloud into the red sequence. Quenching by itself is not enough. And this is why it's really important for us to get into this game of doing this structural decomposition. The headache, though, is it's not easy. There's very few samples we can actually do this for. I'll come back to that, but let me just also go through the finding that perhaps we knew about from earlier studies from Cormandy and many other folk, but I think really came to prominence with the Dorian Fisher work in 2007, is that we clearly see two very different bulge types. We see our compact bulges, our classical bulges, and we see a more diffuse bulge, often what people call a pseudo bulge. And typically blue galaxies will contain the pseudo bulges and the red galaxies may contain the classical bulges. And they may have very different Sersic indices and very different surface brightnesses. But there is no real clear-cut division. Dorian Fisher gave this color versus Sersic index and color versus surface brightness, central surface brightness, where you can see the two bulges are separable, but there is also some overlap in the population, so it's not entirely clean. And one of the reasons that's the case is that often you may have both type of bulges present. You may have a classical bulge embedded in a pseudo bulge with a bar embedded in a disk. And at this point, you start to think, well, how many components do I actually have to fit to a galaxy in order to make it work? And I should also mention Dimitri's study as well of 1,000 spirals in Sloan, in looking at the ellipticals, the classical bulges and the pseudo bulges, where he also highlighted that bulges on the whole follow sequences similar to ellipticals, not precisely, and pseudo bulges follow a slightly offset sequence. And that pseudo bulges share many properties that are consistent with the disk, and the classical bulges share many properties that are elliptical-like, although not perhaps precisely so. It may be that classical bulges and ellipticals both have the same progenitor, but later on evolution, perhaps secular processes, have caused the elliptical and the classical bulges to evolve a little way apart. There is no clean way to automatically separate pseudo bulges and classical bulges. Whether we do it by eye, by Cercic index, or by surface brightness, our classifications do not agree, which makes it very, very difficult. Cercic index was always the great hope, but the Cercic index often comes with the largest error. It's really hard sometimes, particularly have the presence of a nucleus in the very center of that core region. And add to this, you may have the presence of a bar on top. Starts to make the whole idea of decomposition into two components fundamentally flawed at some level. Add to the complexity that the Hubble tuning fork is now completely out of control with all the rise of the dwarf galaxies, and they have a whole host of inner structures. You really are left with the question of how many structures should we try to fit, and how do we form cosmologically representative samples? Probably the definitive study on this has come from the S4G team, the Spitzer team, that provide the Redshift 0 benchmark. It's an absolutely spectacular study of 2,300 or so galaxies within about 40 megaparsecs. And they were able to fit between 1 and 5 components for each of these galaxies using GalFit and GalFit 3, one of the standard fitting codes. And they did it with exquisite care, and very often find a significant amount of light. So in the diagram here, you can see the fraction of light that's associated with the bulge, the disk, a very large amount with the bar, the nucleus, and the nuclear ring. If anyone's read the Slack, you'll see me put out a help message that I'm trying to get someone to do my work for me and to add up all the mass that's been calculated for these 2,000 galaxies and tell me how much actually ends up being in ellipticals, disks, bulges, bars, and so on. I'll show you the answer that we get later on, but you know, that's an interesting one. I'd love to get to this answer by the end of the week, if possible. So let's again come back to the idea. S4G is just on that border of, is it cosmological or not? It's the galaxies within 40 megaparsecs. The environment within 40 megaparsecs may not be representative. 2,000 is a reasonably significant sample, larger than many surveys. But it's possible that our local environment is underdense. It doesn't have a very rich cluster. It doesn't cover all the environments. And so it's difficult to know how representative it is. If we go beyond 40 megaparsecs, or maybe beyond 100 megaparsecs, fitting anything other than 2 components really does become impractical. We've already got about 23 parameters. You add another component, and it's potentially between 5 and 10 parameters on top. If you want to do an S4G analysis, then you really can't be fitting 60 or 53 parameters when you have fewer pixels than you do parameters. And so we're limited to having to fit the bulge component and the disk component. And even then we're limited because of the redshift. If you go to Sloan data with the typical full width half maximum of 1.5 arc seconds, we're limited to a redshift of about 0.05 or 8,000 square degrees. And if you go through the wide field camera and down to HST, then we really are limited to understanding structure at redshift less than 0.1, or with HST at redshift greater than 1.5. So we have this problem that we have low redshift morphologies that are very well defined. And then we have high redshift morphologies that start to look completely different, and almost no data in between, which is where people measure the red and the blue and the change of red and blue, but do that without the aid of any structural information because we just haven't had much until now. The only data set really is the Cosmos data, which is one filter, the F814, and I'll show you some recent work on that. So there's clearly a morphological transformation taking place. There's clearly a buildup of this two-component nature that we see at low redshift. But how is it done? Mergers, gas removal, secular evolution, what's the role of the environment? And why do we have this idea of bulges and disks at low redshift if the foundations for this are not laid at high redshift? Just give you an example of the data that we're looking at. We just show a sample from the gamma survey of what we call a compact bulge disk, a diffuse bulge disk, and a disk, as we go from redshift 0.02 moving out to redshift 0.08, which is as far as we really dare go before we think the data quality is just insufficient. And I think you can see why we're only fitting two components. So essentially, we're fitting a central mass concentration and disk component. And that central mass concentration with forced two-component fitting may contain any of these issues, the classical pressure-supported compact bulge, a nucleus, a pseudo-bulge, an inner or even an entire bar, the peanut boxy central structure. And our implicit assumption is that we just have to assume that on the whole, one of these structures dominates over the mass. So we fit that central mass concentration and then try to classify whether that central concentration is essentially a classical bulge or a pseudo-bulge, or affected by the bar line. I don't think there are good definitions for classical and pseudo bulge. I think 5 astronomers come together with 7 different opinions on this one, and I guess we're talking about a morphologically classified system. So our classical bulge is very much a compact bulge. Our pseudo bulge is very much a diffuse bulge, and I use those terminology going forward. Can structural analysis ever accurately distinguish those things? And those of you that enjoy throwing machine learning at this, generally machine learning algorithms I've seen are only able to recover the eyeball classifications at around about the 80% level. So often with machine learning, you're throwing in a 20% error factor straight away if you're relying on machine learning for your large sample. So where does the mass reside? And this is one of the things that saves us a little bit. If we look at the contribution to the stellar mass density, so it's not quite the same thing as the mass function. We've got high mass galaxies to the low mass galaxies, and we've got the number times their mass here. So the highest point here is telling you what dominates the stellar mass budget. And we can see that spheroids are up here dominating, followed by the disks of the early type systems and the disks of the late type systems. And you can almost ignore everything below 10 to the 9.5. Of course, they're the most numerous galaxies, and there are more galaxies below 10 to the 9.5 by far than above 10 to the 9.5. But if you're interested in the stellar mass, you only need to worry about the ellipticals and the giant spiral systems. And that helps because the giant spirals, the SAs, SBs, are very much dominated, we think, by the classical bulges and not by the diffuse bulges. We also have this interesting balance that the total amount of spheroid mass is roughly the same as the total amount of disk mass. So to first order, we can ignore galaxies with mass less than 10 to the 9, which probably offends half of you straight off, at least at low redshift. And generally the stellar mass is dominated by E's and SABC. So on the whole, most of the central mass concentrations that we fit will probably be classical bulges. So if we actually look at the mass breakdown that have been done by a number of people, starting with Tasker and White, that first put out the results in 2005, but the paper wasn't published until 2011. Our work, Dimitri's work, Lee Kelvin, and most recently, Aaron Robotham here using the latest algorithm, we can see that of normal matter, the stars represent about just under 10%. And of that 10% of the stars, we have something like 37% of the stellar mass in elliptical systems, 18% in classical bulges, 4% in pseudo bulges, and 41% in disks. And I think if we were able, we'd probably find that many of these pseudo bulges are actually bars. And so my expectation is the bars and the pseudo bulges probably together make up that 4%. So by mass, most bulges are classical. By number, most bulges are pseudo bulges. And that's a very important distinction that keeps coming up. People keep on telling me majority of bulges are pseudo bulges, and they're absolutely right. But if you're interested in following the stellar mass, the formation of stellar mass, the generation of photons and energy, it's really classical bulges. The majority of photons, more photons are produced by classical bulges than pseudo bulges, more masses in classical Bulges than pseudo Bulges. And if you put these two together as the spheroid class, then you find we have what, about 55% of the mass in spheroids, and about, put the pseudo Bulges back in with the disks, about 45 to 50% of the mass in with disks and substructures in the disks. So I think the conclusion to me is that there really are two primary processes by which stars form and structure forms, in spheroid formation and disk formation. I want to switch and talk a little bit about energy now, because that's, again, something we I think often don't talk about, but becoming more important as we study spectral energy distributions. And again, apologies for showing my stuff on this, but if we look at the measurement of the energy that is in spheroid systems, so we just take in the luminosity function of spheroids in different filters at different wavelengths and adding up that total energy and doing the same for disks. And then the combination of these two is the total energy being produced by the universe today. The top plot shows the energy output of the universe today from the galaxy population. The bottom one shows that energy that gets released into the IGM after being attenuated by dust and re-radiated in the far infrared. And what stands out is that while we have a 50-50 distribution in terms of the stellar mass in spheroids and disks, clearly the photons being minted and generated by the universe today are massively dominated by the disks, and the spheroids are almost irrelevant in terms of the amount of energy they're producing. And that tells us something we already know, which is that spheroids are made up of old populations and are made up of very old stars. But it means that any model of spheroid and disk formation needs to match the cosmic star formation history. It needs to grow 50-50 amount of mass in the two populations, and it needs to provide systems where there is minimal energy coming out of the spheroids today, and most energy is coming out of the disks. And there have been a number of attempts to crack this one, and they all revolve around something called a two-phase evolution. So we have, from a number of papers, a number of works, this idea that the universe evolved in two distinct phases, a hot phase initially and a cold phase later. I'm just going to go through the Andrews work of this, but many of these papers share similar frame. And there's two axioms. The first is that AGN activity is an indicator of spheroid formation. And the reason that axiom is laid down is because of the Megorian-Gebhardt relation, where we have this correlation between the black hole mass and the bulge flux, the bulge mass, or the bulge velocity dispersion, or the bulge Tversky index. All of these correlations exist. And we take the second axiom that spheroid formation will dominate at high redshift. We know the AGN activity curve from Richards et al., and there have been previous papers by Fan and some more recent updates, where you can see how in terms of redshift, the amount of AGN activity in the universe peaks very similar to the cosmic star formation history peak, and then drops much more rapidly by redshift 1, so we see hardly any AGN activity. So in this two-phase model, we're tying together bulge formation with AGN activity, and we can use the shape of this to tell us the cosmic star formation history of spheroids. So we can scale the AGN activity to the peak of the cosmic star formation history. We can subtract that from the known cosmic star formation history from Edow and Dickinson, and we get the disk star formation history, and then we can run with that and see what it tells us about the stellar mass and the energy. So we have this scenario with time is progressing from the Big Bang through to today. We have the AGN activity that's given by this shape. We scale it up to match the cosmic star formation history, and we say spheroid formation dominates at high redshift, and see how spheroid formation is dominated to about redshift 1.2, after which disk formation is then taking place. Don't take me literally. I'm not saying that absolutely every star that forms has to end up in a disk and no disk stars form, but we're talking about the bulk. The prediction of running this forward, which just means integrating under these curves, gives you the prediction of the buildup of stellar mass. And this prediction with these two axioms gives you this balance where we have 50-50% of the mass in spheroids and disks at redshift 0. So it seems to solve that one. And in terms of the actual energy output, you can look at the bottom plot where we're seeing the energy being produced by the galaxy population in the universe divided by the, shown as either the disk population, the spheroid population, and an AGN population in order to get the ultraviolet right. And you can see how the bulge formation is dominating early on. The disk formation is coming through later on. And then as we get to the end point, we're seeing how the disk is dominating over the spheroids, consistent with our recent observations. So we put the empirical evidence together, and we really are getting this scenario that we have to have spheroid formation very early on, above redshift 1.5, say, followed by disk formation and growth. And when we run with that, we get the mass balance that we see, and we get the energy balance that we see. And perhaps we've always seen this. I mean, if we go back and look at the data from the Hubble tuning fork, and we just order the galaxies in the Hubble deep field in different redshift slices from the brightest galaxy to the faintest galaxy, we can see how up to about redshift 1.5 or 1.3 or so, we start to see things that look ordered, things that do seem to follow the Hubble tuning fork mostly being in place. And then at redshifts above that, we see things that are very clumpy, very bursty, very irregular. And we're seeing highly clumpy, highly irregular compact systems, which I guess I'm arguing are actually our proto-bulges. The problem is this just doesn't mesh with a lot of the information that we're hearing about rotating disks at high redshifts. So here's our picture that we have some kind of collapse event, some kind of merger and AGN activity, perhaps some accretion and gas infall that goes two different routes depending on environment into our disk structures and our spheroidal structures. And that's kind of the big picture that seems to be emerging. And it's not too controversial, except the morphologies of the things at high redshift look nothing like spheroids and nothing like bulges. And so there's a really interesting question, I think, to ask, which is what would a classical bulge or an elliptical look like when it's actually forming in a very rapid, intense burst at high redshift? It's going to be blue if it's forming 100 solar masses a year. If it's forming those in multiple molecular clouds that are going off at different timescales, it probably is going to be clumpy. You can't have that amount of dust star formation without having dust formation, leaving you with a chunky system. If it is a collapsing structure, it inevitably will have some rotation. You really can't collapse anything without introducing some rotation, but you're going to have an awful lot of turbulence from all those molecular clouds doing that star formation. It's not going to look like a clean-cut, nice spheroidal system. Its in situ morphology is going to be very different. Its in situ morphology is going to be not necessarily irregular or a thin disk, but what I'm calling slab-like. And I think we are seeing those. I think we're seeing slabs at high redshift, and they're often called disks. And I think we shouldn't call anything a disk that doesn't have an axial ratio of 1 to 10. They're often highly irregular, but they're quite compact, just a few kiloparsecs across, with vertical scale lengths that are often a kiloparsec. They are clumpy, and they have these very high high VM sigmas, implying that there is significant turbulent systems, and lots of lovely examples of these clumpy galaxies. Are they really proto-bulges? Can they really be proto-spheroids? And so it takes us, I think, to an interesting world. And I like to show this example of Carl Glazebrook's really nice doors review that he did some years ago, where he showed a typical redshift 0 galaxy with a stellar thin disk and a thick disk and a well-ordered bulge. And in his plot below it, he shows the high redshift turbulent disk, which starts to look similar. But I think he made one mistake in his plot. He showed them at the same scale to get the graphic looking right. If you actually take into account that this structure is actually only extending over a few kiloparsecs, you actually have a comparison that looks more like this, that you have this thick, turbulent, irregular looking structure that spatially occupies an extent that is not too dissimilar to the extent of the central bulge component. And I think if you look at the diagram on the left, you would say, yes, that's a disk forming. If you look at the diagram on the right, you'd say that, yes, that's a bulge forming. And it's interesting how important I think it is to be plotting that scale. Now, I'm not going to say that all of the structures that are being seen at high redshift are that compact. I'm aware that there are extended ones as well. But it leads me to ask whether monolithic collapse, fragmentation, and clump migration is potentially all part of the same picture and the same sequence. This idea of a monolithic collapse into a single perfect spheroid, I think, is always going to be naive. You can't collapse that much without having some introduction of rotation. You're likely to have fragmentation, and within those fragments, you're likely to form clumps. And then the rest of that collapse is something that you may term clump migration. So I'm also really interested in learning from the high redshift community whether this monolithic collapse into fragmentation into clump migration are actually 2-3 different processes, or whether they can be linked into a single process to make the things we're seeing at high redshift, proto-bulges and proto-spheroids, as the energy model suggests and the mass breakdown that we see locally suggests. So we have a lot of physical process that we talk about. We have, I guess, hot processes and cold processes. We have the monolithic collapse, the major mergers, and the AGN activity, which are all generating vast amounts of energies and probably do lead to spheroids and black hole formation, and maybe star formation shutdown. And we have a whole myriad of cold processes, some of which fall under the bracket of secular. Another term that's very poorly defined. To me, secular evolution is only something that happens inside a galaxy, which means it doesn't include accretion and minor mergers or tidal interactions. For others, secular evolution includes all of those aspects. It's anything that happens after some period of time. But we probably have a high redshift world which is dominated by these hot processes, and a low redshift world that's dominated by these cold processes. And in there is why we have these two formation and migration pathways. Somewhere in there may be fragmentation and clump migration that leads to the clumpy knots and the bulges. And I think it's a really interesting question as we have a monolithic collapse into small components that are fundamentally independent and then they merge together, or whether you'll have a single monolithic collapse that fragments internally into clumps that then continue to merge to form the bulge. And to me, that's a really interesting physical difference that hopefully we'll get to with JWST and other facilities. So the very quick practicalities for the experts out there is the whole deal of doing bulge disk decomposition can be a nightmare. Some codes struggle, and depending on the initial conditions that you start, you may converge to a different bulge disk solution. And so we have to move to a world where we're now using much more clever minimization algorithms using MCMC and having to run them essentially on supercomputers. When we do get into processing on Euclid and Roman, we are going to need millions of CPU hours to do robust bulge disk decompositions of hundreds of thousands of objects in order to really add structure to the equation at any redshift. And the other thing, in case anyone's not aware of this, is how unstable the Hubble Space Telescope point spread function actually is. We've been struggling and grappling for about 4 years, interacting with the experts at the Space Telescope Institute, and we're basically unable to model the PSF to better than about 80%. So we can only remove 80% of the light in the perfect case of an independent isolated star, a tiny TIM PSF in the raw data, subtracting it. And the problem is the telescope breathes. HST breathes periodically, and that breathing causes problems that makes the PSF unstable. So we can only believe bulge parameters from the Hubble Space Telescope at sizes greater than 0.1 arcsecond, which is right at the limit of where you want to be. Many bulges seem to be smaller than that. In order to do better, we're really going to need to understand JWST, Euclid, and Roman PSFs much better than Hubble, and hopefully being in the cooler environment of L2 will really help with that. It also makes me worry a lot whether we will ever be able to realize the hope and do decompositions with multi-conjugate adaptive optics, whether we'll be able to understand the PSF sufficiently well to really get down and realize the resolution we hope to get with the ELT and so on. Hopefully that will be possible. So let me go through a couple of results. Completely lost track of time, by the way, but I'll just keep blathering. And two results I want to go through is the growth of mass and emergence of structural components. We already have the mass breakdown at redshift 0, which seems stable across about 5 or 6 independent studies by different people on different data sets using different codes. Can we start to do the same thing with the Cosmos data? We don't think we can use machine learning yet or any automated way for doing the classification. So we've had to go through the process of eyeball classifying 36,000 galaxies in Cosmos by 3 classifiers in an incredibly painful process. And we find that as we look at the fraction of galaxies, and I'm sorry the labels aren't here as to what type these are, It's just off the page. The gray is the ones that we can't classify because they just don't adhere to a Hubble tuning fork. And that's the important one I want you to look at. You just see that Hubble tuning fork, what we call elliptical spirals, regulars and so on, are consistent. But as we go out to round about a redshift of 1, we suddenly find that nothing looks like a Hubble tuning fork. Not nothing, but very few things look like a Hubble tuning fork galaxy anymore. And this whole notion that we just have spheroids and disks kind of break down. It might mean that they're proto-disks and proto-spheroids, but they stop looking as clearly defined as that, which makes it particularly hard. We can compare the classification accuracy of the classifiers, and we can look at the agreement between them. And we can see that as a function of stellar mass and redshift, we do better for the higher mass systems in yellow. But we actually do okay. We actually do better than 90%, so 95%. I think red is where you get down to about 90% or less, and there's only a few red cells. So on the whole, we're getting tremendous agreement between our 3 independent classifiers with the HST data. The separation into pseudo bulges or diffuse bulges and compact bulges is hard. We use the Godotti criteria, which is basically the Cormandy relation, which ends up being a line cutting through the distribution, defining the dark blue as the pseudo bulges and the gold ones as the classical bulges. Gives you an example of what that classification looks like, where we have the classical bulges on the left and the diffuse bulges on the right. On the whole, I think it's getting it right, but I think I'll be a bit dubious about this one. And maybe this one has both components embedded in that center, and it's an example where we have both a diffuse and a compact bulge. But on the whole, I think we're having compact bulges separated, diffuse bulges separated, with some uncertainty introduced. We fit these with the Prophet code, and we can get the profiles out. And again, the pseudo bulge and the classical bulges generally do look a little bit different, with the mean profile much steeper for the classical bulges and the pseudo bulges. And we can look at the mass functions of these types from redshift 1 down to redshift 0.08. I refer to the papers to look at this in detail, and I just take you to the final plot, which is really the growth of mass of different types. When we integrate those functions, we see essentially stability in the disk population, the total amount of mass in the disk, just a slight rise and a slight fall. The ellipticals we see rising quite significantly, factors of 2 or more. The bulges rising even more severely, and the pseudo bulges rising even larger. So we're really seeing at low redshift this idea of the emergence of bulges and the emergence of spheroids and the stability of disks. And again, that seems to be in the opposite direction to what I was saying earlier when I was saying that all star formation early on. But of course, this diagram is not talking about when the stars were formed. It's talking about when the structures were emerging. And I know I use the word emerging, not forming, because if you do suppress star formation in that disk and you do remove dust, then whatever you have in the center becomes more obvious than it does before. And so the question really is what's the right way to classify a galaxy? Do you want to have use its final morphology and find a way to use its final morphology back in time? Or do you use its in situ morphology? And do you accept that these may vary or will vary at some point? And although these things don't look anything like spheroids at this redshift, these are things that are destined to become spheroids in due course. And so the only way to get up to that is a new way of looking at data sets that's coming around, which is not just doing a structural decomposition, but doing a joint decomposition, folding in the spectra or folding in the colors at the same time. And see the talks by Lorenzo Caceres and Konstantin, who I think use C2D in a similar way that I'm going to describe here. So we're trying to use a code that does, like MagVis, like Segal, that does SCD fitting, combined with a galaxy decomposition code and a source finding code, and doing this all in one go in this code called Profuse, which has just been put out. The papers on AstroPH and all codes are on GitHub. Very quickly, Prophet does the normal thing of doing the MC-MC fit with the images. So you have the data here, you have the model, and you have the data minus the model, and you can get the various fits out. And we're doing a full MCMC chain, so you can really see whether you have convergent, and the code can fit a variety of our familiar and favorite profiles. That's the standard profit code, quite similar to Galfit, quite similar to Gym2D, except it's using a very, very sophisticated MCMC, which means the code is a little bit slower than some of these other codes. On the prospect side, where we're looking at the SEDs, you can have a nice distribution where you've measured the light of a particular galaxy, and we can decompose that using the stellar population models in order to reconstruct the star formation history for that population. And when you do that for a population of 16,000 galaxies, you find you can take this population at redshift 0, you can do the SED analysis, and from that you can reconstruct the entire cosmic star formation history that agrees quite well with the core sample studies. And of course, there are other papers, Lager and so on, the Prospector, and that are also doing something similar and managing to recover this.
Simon, now, maybe we can start wrapping up.
Yeah, thank you. Yeah, I did. So Profuse is putting all of this together, and here you can do a simultaneous UGRIZYJHK fit, where you're doing that pixel-to-pixel comparison, but you're doing it for a bulge in the disk, and you're also getting the bulge light of the bulge and disk out, which means you can reconstruct the star formation history of the bulge component and the disk component. Let me get to the summary plot, which is when you do this, you get your cosmic star formation history, which seems to tell us that we have bulge formation happening very rapidly, very early on. All of that bulge light is forming at very high redshift above redshift 2, and then the disk light is coming through and being generated much, much later. So again, this supports the conjecture that all or most star formation at high redshift ends up in spheroidal systems, even if they don't look like spheroidal systems at high redshift. I won't go through the future. There's 3 slides there, but we know JWST, Euclid, and Roman is coming. We're going to need to have halo masses to understand the halo environment. And I said absolutely nothing about AGN, which is probably a critical part of the process. So let me just come to my summary slide and try to reiterate a few things that I think we as a community have established over the last decade or so. The stellar mass really does reside in 2 clearly defined components, spheroids and disks, which really does imply 2 distinct formation mechanisms. I would argue that pseudo-bulges and bars are subcomponents of the disk, and when I add up these disks, the stellar mass component, I put the pseudo-bulge and the bulge the bar mass back in with the disk. And these have been formed by secular evolution processes acting on the disk. Energy considerations, which I find very compelling, really suggest that most star formation at redshift 1.5 has to end up in spheroidal systems, regardless of what they look like. And I really wonder whether the high redshift and high V of sigma compact slabs we're seeing are likely proto-bulges and proto-spheroids, even if they don't look like it. Spheroid morphology, nevertheless, does emerge strongly at redshift z = 1. Maybe we're never going to see a spheroid forming that looks like a spheroid is perhaps the key point to make. And I think the last point I'll stress before I better shut up is the monolithic collapse, fragmentation, and clump migration. I'm really interested in what some of the high redshift pundits, theorists, and experts think of the idea of this being a single chain sequence that actually leads to that formation of spheroids. And I'll thank you very much for your time, and I'll stop there.
Thank you. So before we start with questions, I would like to remind everyone that if you don't want to appear in the recording, please keep your camera off and just write your questions in the chat, and I will read them out loud. Otherwise, please feel free to raise your hands and we will unmute you if you have a question, or just write it in the Slack channel. And again, we will read it. So maybe while I don't see raised, maybe Federico Lelli has a question.
Hello, very nice talk. I have a question regarding the evolution of morphologies with redshift, because as we move back in time with HST, we are of course probing bluer and bluer bands. So I was wondering whether this is taken into account when you trace the evolution with morphology, because as we know, the structural components are most clearly visible in the near infrared. That at this point, until we have JWST is not clearly accessible at IZ?
No, that's a great question, and I think that was the entire motivation in a way for the goods program that Mauro Giuliasco led, was to explore whether the fact we're seeing these changing morphologies is merely that we're looking at the ultraviolet light. I think the upshot that came out of that is that while that does explain some of it, it's not the dominant factor. It ended up being a little bit of a red herring. At least in the stuff I'm showing going out to redshift 0.8, we're looking at the F814. We're not yet looking at ultraviolet light shifting in. So our morphologies and our structural decompositions that we're doing on the Cosmos data certainly is looking at that 4,000 angstrom longer light, where on the whole morphologies don't change. But I think going beyond that, beyond redshift 1, I kind of absolutely agree, because if you add in the fact that the star formation rate is going up as well, you're likely to see much more irregular UV morphology. And I think that's why we're all absolutely hanging out for JWST. That's just going to open up that long wavelength regime, so we can look at high redshift as we look at low redshift.
Thank you.
And we have a question from Bruce Selmergreen as well.
You're muted, Bruce.
Did that work? Okay. Hi, thanks. Very nice talk. I'm wondering how thick disks of today fit in to your point number 4. Thick disks, as you know, are old. They have high alpha. They look a lot like bulges, and they're extended. They go out to, say, the solar radius in the Milky Way. Most of today's spiral galaxies have thick disks. So it seems that there had to be a disk formation at high redshift that stays as disks today. They didn't all go into bulges. And when you see the smaller sizes at high redshift, they're perhaps just the brighter inner parts of things, including bulges, but things who have extended parts that will end up as disks today.
Yeah, no, again, I think that's really interesting. I know my memory and history of the Milky Way thick disk is that it has come and gone a little bit, and is also the amount of mass associated with it has varied from sort of very little to a medium amount to not so much. I'm not quite sure where we're up to on that discussion. And also galaxies have been shown to have more than 2 disks, not just a thin disk, but a thick disk. I'm not sure I have any data that can comment on that. I think there are probably better people who study locally. In terms of conceptually how it fits in, yeah, I agree. I mean, I wonder whether the images that we're seeing currently with HST or other are just seeing that central region. And when we're able to push the lower surface brightness, that 1 + c is 1 + c to the 4 is such a massive factor that we will see some of these compact things as being more extended. And that maybe we are seeing, the thick disk is somehow the vestige of that slab. But how that thick disk then separates, partitions its energy into a pressure supported bulge and a surrounding disk, you'd know better than I, Bruce, as to whether that's viable or not. So I don't really have an answer, but I understand the question. I wait for the empirical data on JWST to see whether we see more complex structures when we revisit the objects that we're familiar with. But I guess I would imagine that the slab is not. Maybe again, a Milky Way expert can remind me whether the radial scale length of the thick disk is sufficiently shorter than the thin disk, or maybe Bruce, but I mean, that would be the obvious thing to look for.
Yeah, nearly 100 local galaxies in the S4G survey were studied for their thick disk, and it's not a small component typically. This is in papers by Sebastian Kammerer as the lead author. So yes, a lot more observations, even of the local galaxies, is needed to understand that.
Okay, so we still have time for a couple of quick questions before we need to move on. So there is one by Michael Rick.
Yes, I was going to ask the distribution of ages for the stars in the models generally. I noticed, I'm surprised that, it's only at roughly redshift 1 that bulges really begin to be clearly defined. Are the ages of the stars that comprise those bulges significantly younger, say, than the halo and globular clusters, like 8 to 10 billion years?
I mean, I think I would worry a little bit about the precision of the ages. If you're talking about this kind of plot and where we've reconstructed the cosmic star formation history from the light and reconstructed essentially the ages of the populations, which is implied by this, I'm not sure, you know, that I'm not sure I would ever believe this at a very high level of accuracy. I think what we're seeing with a diagram like this is that when we do our profuse fit-in, we're fundamentally seeing that the light has to be old. Old is, you know, 10 billion or so years ago. And I don't think I would ever argue that it, you know, may be as old as globular clusters or less old, or get into that kind of level. I think that's where you've got to talk to the people doing individual studies of individual stars and actually doing the extraction of robust ages. It just gets harder, right, to recover ages the further you go back. So I couldn't say whether the stellar populations that are implied in these bulges are as old as globular clusters, which I think was your question.
Great, and one last question by Paola Di Matteo.
Yes. Hi, Simon. Thank you very much for this talk. About the thick disk in the Milky Way, indeed, when I was looking at your slide, I think it was 28, where you were showing disk, the sketch with the disk at high redshift, and then the evolution to the low redshift with the thin disk. Yes. Yes, you passed through this. But anyway, in fact, in the Milky Way, the thick disk, yes, this one. When you look at the right column, my first reaction was to think that what you see at high redshift is indeed very similar, let's say, at least in size, in what we would call a thick disk today in the Milky Way. The alpha-enhanced thick disk in the Milky Way, which is metal poor, has a scale length of about 2 kpc and a scale height of about 1 kpc. So it's extremely more compact than the mean, let's say, the thin disk, at least, the mean scale length of the thin disk. So I was wondering, in some sense, it was similar to the question by Bruce, how the thick disk enters into this evolution, and how much of the spheroid problem that we possibly have at high redshift can be relaxed somehow if we include the thick disk into the picture.
Yeah, no, I think that's really interesting to consider. I mean, I guess if you consider this structure here, what I think both you and Bruce are saying is there room for this structure, out of this structure, for both a thick disk and a compact bulge to emerge? And it may well be that the clumps can migrate within this to form that compact bulge, but some residual relic of this structure remains, so that eventually becomes a thick disk. I'm not a theorist or a dynamicist, so I can't really say whether that's plausible, but I think that might be the scenario that I'd be looking at, that this is the protostructure that gives rise ultimately to both the compact bulge and a thick disk component. And the fact that you say the scale length is so much shorter of a thick disk, you know, it seems to argue that maybe you can get partition of energies in some way, some dynamical relaxation that brings in the clumps and leaves something behind which becomes a thick disk.
Thank you, Simon. Unfortunately, now we have to move on. So if you have any further questions, please feel free to write them in Slack, and then Simon can answer to you there later on or discuss during the discussion session.